Alright, so we're back, part 2 of our series where we're going to be discussing the topics in line with the CSEC Chemistry course. So again, I am Mr. Thomas, founder of Buckle Down Tutoring Services. And we're going to dive right into mixtures and separations. Now, this part says, complete the following table which compares a pure substance and a mixture. So you say to yourself, what's a pure substance? What's a mixture? Now, in terms of the composition, it says the mixture, we don't have a response in this table, so we're supposed to complete the table. But we see that the pure substance is fixed and constant. We're talking about the properties, whether the physical or the chemical properties, they're fixed and they're constant. Let's zero in on what we mean by that. It's the same throughout. So pure substances are basically divided into elements or compound, right? And so these have a fixed and a constant composition, whatever makes it up. And so if you have a pure substance, take for example pure water, it should have the same physical property if I have pure water. So you cannot have pure water, and your pure water in terms of the boiling point, it's boiling at 100 degrees, and I also say that I have pure water, but my boiling point is 98 degrees. No, that is not, one of us would not have a pure substance, and we know pure water boils at 100 degrees. So the composition of a pure substance is fixed and constant. If someone in the Caribbean has gold and someone in the United States also has gold, then the same composition that the person in the Caribbean has the gold would be the same of that person who is in the US. But when you look at a mixture, the mixture, it varies in terms of its composition. It's not the same throughout. And just like pure substances, we have two types of mixtures. We have homogeneous mixtures and heterogeneous mixtures. We're going to be looking at that later on. Properties. The properties are fixed and constant. And as I said before, if you have a boiling point for water, once it is pure water, another person who has pure water as well, it should be the same. That's one way of actually trying to figure out if a substance is pure. We normally look at the boiling and the melting point. And when something isn't pure, we say that it contains impurities. So if water has impurities, impurities will actually affect the physical properties such as the boiling and the melting point. So if impurities are there in your water, it will not boil at 100 degrees Celsius. It actually causes the boiling point to increase, so it's higher. Now when you look at a mixture, in terms of the property, the components in a mixture, what they will do is to retain their property. So say for example soil and water, the soil will retain its property and the water will retain its property. And so at the end of the day, you do not have a situation where the property is changed. So the mixtures, the components that are a part of the mixture, they retain their own property. The next question speaks to distinguish between an element and a compound. Now we know, ask yourself, where do we find the elements? What is it that we look at? We look at the periodic table. And the periodic table categorizes elements into groups where we have those columns and we have rows which represents the period. Now on your periodic table you can be either a metal or a non-metal. Where do we find the metals? Where do we find the non-metals? You should know this. The elements, they cannot be broken down using any physical or ordinary physical or chemical process, right? So we cannot break it down any further using, it can be broken down, but you cannot use any ordinary physical or chemical process to get it further divided or further broken down. While a compound is basically, it's a combination of two different elements or two different atoms of the same element, and one of the things that is happening in the compound is that there is some form of chemical combination. So they are chemically combined. Usually the compound that is now formed due to the different elements that make it up, it has a different property than the elements that are the constituent of that compound. So take for example sodium chloride, which is table salt, is a compound, and later on you're going to be able to identify the types of compound, ionic or covalent. Now sodium chloride is definitely an ionic compound. We're not going to get into that, but one of the things that we want to look at is the two elements that form this compound. Please note, we say sodium chloride, and so we use that IDE name for the nonmetal when it is bonded to another element. So we know it's chlorine. When it's now bonded to sodium, we say chloride, right? Now chlorine is like a poisonous gas. Sodium is also a metal. We would not dare to consume sodium by itself or chlorine by itself, because those properties will be harmful to us as human beings. Yet still, when they combine chemically, we get sodium chloride, which is something that we normally use when we are preparing our meals. We put it in our pot and to prepare our meals. We're eating our banana chips and we have it salted. Sodium chloride. So we can consume that compound because the properties of the new compound is much different than the individual components or the elements that make it up. The next part of it says, using each of the following properties, give the difference between a suspension and a colloid. Now, suspension and colloids are actually heterogeneous mixtures. The other branch or the other type of mixture would have been a homogeneous mixture, which involves a solution. Now, a suspension and a colloid, particle size. When you think about it, in terms of particle size, a suspension would have larger particles than a colloid. In terms of sedimentation of particles, meaning it will settle out, the suspension, if left undisturbed, again, prime example, soil and water, the components will settle out. While for colloids, the components will not settle out. You won't see a difference in the components that make it up. Passage of light. It is not possible for light to pass through a suspension. While most colloids, what you find that they do is that they scatter the light when it is actually going through. Now, the next question says, what is a solution? Earlier on, we mentioned that a solution is actually a homogeneous mixture. And that means the homo means the same. So when you look at a solution, you're not able to distinguish between the components, right? So it looks uniform. No, it's a homogeneous mixture, one of which you have different components that makes it up, and usually one is a liquid. Now in chemistry, you're going to find that oftentimes, if you want to get a little bit deeper, there are two things that make up the solution when you're dealing with a liquid. The solvent, and that's the substance that is doing the dissolving, and you know the common term, water is the universal solvent. So we use water, and it's not only water that we can use to dissolve things, but water is the universal solvent. We also have the solute, and the solute is a substance that is being dissolved. The thing about it, when water is the solvent, we call that an aqueous solution. So when you're looking at a chemical equation in chemistry and you see that little subscript and you see AQ in bracket, what that is saying is that that substance is dissolved in water. So if I have NaCl, which is sodium chloride, and I put in bracket AQ, what that should tell the person reading is that this sodium chloride is now dissolved in water. Usually, in terms of concentration, the solute is a larger concentration than that, meaning you have more particles of the solvent, right, than the solute. So the solution contains the solvent has a larger concentration than the solute. Now when you think about the term solubility, in solubility, it's the amount of solute that is able to dissolve in a solvent at a particular temperature. Now, temperature affects how solutes are capable of dissolving in the solvent. So when you have the increase in temperature, you're adding heat, what you find is that the temperature causes the particles to get more kinetic energy and they move around. The water is now able to break apart those ionic compounds and cause it to dissolve more. So as you increase the temperature, solubility also increases. So sometimes we're there, and this is a misconception, you may see some white flaky stuff in your water. And you know your grandmother say, here, in Jamaica, them say, go and boil the water to get rid of it. And so you boil the water, you recognize that the flakes just like they disappear. And you say, yes, the water good for drink. You get a glass and you put it in the freezer. And when you place it in the refrigerator, after a while and the water starts to cool, you recognize that you see the white flakes coming back. And you say, where it come from? Now what you have done with the heating, you actually increase the solubility. So now you're able to dissolve more of that white stuff in the water, so they're not visible anymore. When you reduce the temperature by putting that water in the refrigerator, what you have now done is that you've caused the temperature and the particles of the solute to come out of the solution, and they're now more visible. So boiling the water doesn't get rid of the chemicals that are inside. Sometimes what you're doing is to just causing it to dissolve more. Now this question, solubility curve. It says the graph below shows the solubility of compound Z, right? It varies with temperature. Use the graph to answer the following questions. Now we know when we look at this, we're seeing on the x-axis solubility, sorry, the y-axis, my bad, solubility, and on the x-axis, we're seeing the temperature. Now, this is 1 centimeter, so when you think about the scale, 1 centimeter to 10 degrees Celsius on the x-axis. What does that mean? Each of these points is basically 2. So we have 0, 2, 4, 6, 8, 10. On the y-axis, it's similar. 1 centimeter to 10 grams. So each stroke is 2, 4, 6, 8, 10. So each stroke is actually 2 grams. Now it says, what is the solubility of Z at 28 degrees Celsius? Now CXC and these questions, they can ask you what is the temperature, or they can ask you what is the mass in terms of grams. How much is dissolved at a particular temperature? So the question can give you the temperature and ask you for the mass that it dissolves, or give you the temperature, or give you the mass and ask you for the temperature. So when we look at this graph, the first question says, what is the solubility? This is our curve. And it speaks to the fact that, as we said before, as temperature increases, the amount of solutes that can be dissolved will increase. So solubility increases. Some students will make reference to the fact that they are directly proportional. So we find 28. So 28 would have been right here, and we carry it up right to this curve, and then we bring it right across. Follow. For ease, when you're in an exam or you're doing a test, use your ruler to get accurate, because sometimes the lines can be a bit tricky. So you're trying to follow, place your ruler to get the line straight, and then you bring it across to the y-axis. So we're seeing when you have the substance or the solution at 28 degrees Celsius, it is able to dissolve 18 grams of substance Z. Yeah? Now, once you're referring to the saturation or saturate, you know, the weather person will say that the clouds become saturated. So the water vapor that makes the clouds can't hold anymore. So we have precipitation, we have rain, right? The soil is saturated, so we have flooding. The soil is not capable of allowing water to seep down any further. So it is the water retention, it reaches capacity. And so the water holding capacity is there, and so you have flooding because the soil cannot have any more water going down. Now this substance becomes saturated when it cannot hold anymore at that particular temperature, and we use the curve to tell us where. So first they gave you the temperature to find how much. Now they're giving you the mass for you to find the temperature at which it would be saturated. And this is in 100 grams of water. So we find 26. So 20 is right here, 22, 24, 26, and we go right across. And as I said before, use your ruler, right? And so that will take us to 44 degrees Celsius as the temperature where it is now saturated. Now if your curve, any point above the curve, we consider that to be super saturated. So if you have a point, normally the curve on the curve itself is when it is saturated. So if I made mention that at 20 degrees we have 20 grams, this is above the curve. So this simply means that this is super saturated. It would have been right here, right about, when we are looking at this is basically, to be exact, about 12, 14 grams. So if it having 20, it means it having more than it would have been saturated. So we call that super saturated. Now, if at 20 degrees Celsius it has in 10 grams, it's below the curve, we now say that it's unsaturated. It still can hold more, right? Now our next question says, what mass of Z would crystallize out of solution containing 100 grams? Remember I just spoke about the fact that, you know, sometimes you see that white flake stuff. That's what we're talking about. So the temperature was, if it was saturated at 76 degrees Celsius, right? And if the solution is cool to 10 degrees Celsius. So we're going to go back and look at our graph. So for 76 is right here, and we go right up to here. Then we bring it across, and as I said before, use your ruler. So it is saturated any point on the graph, on the curve rather, that's when it is saturated. And one of the reasons for me not to actually be showing you in terms of and just talking is because I want you to be doing the work. You have to get active, right? And not just to write the answers coming from the video. So you should have your workbook working with. So the 26 the 76 degrees Celsius will allow the substance to be saturated, and it will be holding 54 grams. Now we said that we cool the substance to 10, right to 10, which we now recognize that it would have been 12 grams. So from 54, it's holding 54 because, again, we know solubility is affected by temperature. So if we increase the temperature, we can dissolve more. In this case, we decrease the temperature. So the amount of solute that is capable of being dissolved is going to lessen. So you're going to see come out of the solution. It's going to crystallize out. So 12 grams. So we now know how much between that fell out. We will subtract the 12 from the 54, and you can tell me how much you get in the comments. So that's the calculation for that question. Part 4 says, what is the minimum mass of water that would be needed to dissolve 45 grams of Z at 62 degrees Celsius? The next question says, what is the minimum mass of water that would be needed to dissolve 45 grams of Z at 62 degrees Celsius? So we're going to go back and look at our graph. For 62 degrees Celsius, we're at, so look keenly, we're at about, it's not directly on the line, so we're at 39 right here when we go across. So we're at 39 grams because it's not directly on the line here. It passes through the center. So we know each is 2, so in between would have been 39 and then 40. So I'm going to jump now to a Word document to show you how you can work this out. So here we are on our Word document, right? And we know that that graph was based on 100 grams of water. So that is normally the constant that we use. But there's something else that can affect solubility. So if we keep the temperature constant at 62, but they're asking us what's the minimum amount of water that we need to be able to allow for 45 grams. So when you think about it, at 62 degrees Celsius, right, it was capable to hold 39 grams of solute Z. And while we were at that 62, we had a volume, or in terms of mass of the water that we were using, the mass of the water was 100 grams. And from this we can get a conversion factor. We know when we have 100 grams of water, let me use the solvent. So when we have 100 grams of the solvent, it is capable of, at saturation, hold 39 grams of the solute. So the question is, we want to find how much solvent is needed for 45 grams. So the solvent, how much is going to be needed for 45 grams? And even with this, guys, you can look at this. So when I have 100 grams of solvent, which is water, I can able to dissolve 39 grams of the solute. Would I need more or less solvent to dissolve this 45 grams? Remember, the temperature is constant. If your answer was yes, you're indeed correct. So we need solute. So we have 45 grams of solute. We want to find out how much solvent would be needed. We're going to be multiplying this from this that we have right here. And I don't teach the cross multiplying method. We get a conversion factor from this, where we're going to be creating a fraction. The rule is any unit that we have here that we start with. So we have grams of solute. Whichever unit is there, we place that as the denominator. So from these two, we're creating a fraction. So ask yourself, who is going to be the denominator? If you had said 39 grams of solute, you're correct. Right here, we're seeing that. Who would be the numerator? 100 grams of solvent. So 100 grams of solvent we now have 39 grams of solute. If you do that math, you know with this, what you do, grams of solute will cancel out grams of solute here, leaving our answer in grams of solvent. And we know that solvent is what is doing the dissolving. And so it's basically answering our question. So what is this saying? It is 45 times 100, which is 4,500. 4,500 divided by 39, and you will get, when I worked it out, 115.4. And you can try it. But what is this? This is going to be, you said it, definitely, grams of solvent. Remember, solvent is what you use to do dissolving. So if I have 45 grams of the solute of substance Z, I am going to need 115.4 grams of water for it to be saturated at that same temperature of 62 degrees Celsius. For this part 5, it says what mass of Z would be required to saturate 350 grams of water at 55 degrees Celsius. Now remember, the mass of water that we're using in our experiment with our graph is 100 grams. So 100 grams in terms of 55 55 is in the center here, which brings us right up here, and it's not in line with it's not touching the line yet, so we are looking at about 33. So at 55 degrees Celsius, 100 grams of water will be saturated with 33 grams of solute Z. We are asked to find out what would it be if it was 350 grams of water instead of 100. What is the amount that would be needed to saturate that mass of water? So again, we're going to jump over to our Word document, and we're going to be having the discussion, and we're going to be working it out. So what do we know? We know when we have 100 grams of solvent, it is capable, or it is saturated at 55 degrees in terms of holding 33 grams of solute. Now the question is, remember the temperature is being kept constant. If I now have 350 grams of water, which is the solvent, would I need more or less solute to saturate it? Ask yourself that question. So when I have 100 grams, for it to be saturated, I need 300 grams of the solute, which is substance Z. So if you said we need more, definitely. So we now have 350 grams of solvent. That's what we have. We're going to be multiplying the same concept. This is our conversion factor, guys. And we said before, we're going to create a fraction from this. So instead of doing the cross multiply, this eliminates any mistake. The fraction that you create, one of these will go as your denominator, the other goes as your numerator. What influences who goes as the denominator is the same unit that is here. So grams of solvent is going to be what we place as our denominator. So we have 33 grams of solute. That's going to be divided by the 100 grams of solvent. It's a little bit distant from the word. Alright, so basically let me see if I can just carry it up. Alright, reduce the lines, spacing. Yeah, it's a little bit closer. So again, we would recognize that the grams of solvent will cancel out grams of solvent, leaving our answer in grams of solute or mass of solute, and that's what we wanted to find out. We want to know how much it's going to be holding when it is saturated, which simply means this in itself is 350 times 33, which gives us, when I worked it out, we got 11,550. And then we're going to divide that by 100. You know, you can bring the decimal places to the left. And so we end up with 115.5 grams. And what are we going to be having? Grams of solute. So this is the amount of solute, grams of solute Z, substance Z, for it to be saturated if we have 350 grams of water, the solvent. Now the next question says, you are given a container of seawater which also contains some sand. You're to draw a label diagram of the apparatus you would use to remove the sand from the seawater. And we know when we're looking at separation technique, one of the things that you want to look closely at, or what will help you to identify the method of separation that you'll use, you look at the two substances, the mixtures, or the components that make up the mixture, and you play around in terms of the property. Now we know that in terms of the seawater, the size of the particles, the seawater has in salt that is dissolved in it, while if you mix it with the sand, so the sand retains its property, and the sand will not be able to be dissolved in the seawater, right? Now we can use the method of filtration. So the water particles are large enough, or rather small enough, to pass through your filter paper, but the sand particles are not. So we're going to quickly move to a Word document again, and we're going to be showing you just a quick illustration of what you would have been required to draw. Alright, so we are on our Word document. So just bear with me. So we go in shapes, and we can use the line. So right here, what I'm doing now is creating my filter funnel. So my filter funnel. Now when you're basically carrying out the experiment with the filter funnel, one of the things that you want to do is to fold your filter paper and place it inside. So you can fold your filter paper in two, and after doing so, you're going to be placing it inside the filter funnel. Now to prevent you from spilling the contents, so you'll have the contents of your mixture with your sea salt and sand in a beaker. So say for example, you have your beaker here, right? So inside of this, you have your contents of your mixture. Let's put in a few of these. So these particles will represent that of the sand. And of course, you're going to be pouring it. As I said, this is going to be lined with a filter paper. Let me just use another color for that, so that we see the difference. And so once you pour, kind of look far from it, once you pour the mixture in with the sea water and the beaker with sand, we say that we're going to have a situation where the filter paper has some pores that will allow the sea water to pass through, but not the sand. So we'll basically have another beaker here, And this beaker will be collecting the seawater from our mixture. So we basically have that. So they said a label diagram. You can label some of these. You can do the labeling. We would have had our filter paper. We also have our filter funnel. And this part of the mixture that doesn't go through the filter paper begins with an R. Do you know it? If you said residue, then you are correct. So these are residue. Now we also have our beaker, and we also have this part, which is the sea salt coming through. And I'm just giving you an opportunity to label your diagram. This is the apparatus. This would have been the filtrate. So the filtrate will contain the seawater, while our sand particles will be left trapped in the filter paper. So when you're thinking about a method to separate a mixture, we look at the property, maybe what one component of the mixture have that the other. So this one, the sand particles are too large to pass through the filter paper. The next part of the question, well, the next question says, name the method you would then use to obtain pure water from the seawater. Now the seawater will contain salt, and again, one of the things that you want to utilize in this method, you have to think about the solute in the solvent. If it is one that will decompose upon heating, it will influence the method. But we know salt, it basically has a temperature that in terms of its melting point is very high because of the bonds that are between the sodium and the chlorine. There's electrostatic forces of attraction between the positive cation, the sodium, and the negative anion, the chlorine, which allows you to have high energy, which is required to break that bond. So high temperatures is needed. So with that being said, it doesn't break down upon heating. So a method of simple distillation can be used to separate or get pure water, because what you're really going to be doing is to separate the water from the salt. It says, name the key component of the apparatus used to obtain the pure water in 2 above and explain its function. One of the components that is used, we call it the Lebesgue condenser, and what it will do is to cool the vapor after it is removed via heating the solution with the seawater. And I'm going to just go back to our document to show you what I'm talking about of a simple distillation diagram. Alright, so if we're looking, this is a setup of the simple distillation. So we have our salt water, the seawater would be here. We have our Bunsen burner providing the heat, and we said that this can be used with the separation of or obtaining pure water because the salt does not decompose upon heating. So while you heat, we're going to be having the water becoming a vapor and it will rise. So hot air rises, the temperature is here. CXC likes to bring this diagram as a multiple choice. Sometimes they put the thermometer on the outside, they put the thermometer in the liquid, they put it different places, they don't have any thermometer in here at all. Now please note that the thermometer is not suspended in the liquid, because what it will be doing is to monitor the gas. So the vapor that is here, pure water boils at 100 degrees. So when we are looking at the temperature here, it should be 100 degrees. And again, we talk about that condenser. This is the part that is critical to the simple distillation. Now we have water which is cool going in. Also very important, look at where the water in and out. The in is at the bottom, the out is at the top. So this is being circulated just like the concept of a radiator in your car or your motor vehicle, how it cools the engine. So what it does, the vapor that is in this tube, in the condenser, is going to be cool and is going to be changing back. Condensation will happen, and so we now collect our distillate, which should be pure water. The next part of the question says you are given a second mixture of ethanol and water. What technique would you use to separate the ethanol from the water? Now, ethanol and water, we call them miscible. That's a term. Miscible meaning that they are capable, when two liquids are able to mix, we use the concept of fractional distillation. Right? Ethanol is capable of mixing with water, so we consider them to be miscible. So what we'll be using is a technique known as fractional distillation. Now, complete the following sentence. Ethanol and water are separated based on their different. Now, one thing that we use is the fact that they are different liquids. And so we focus on what we call the boiling point. And if you can recall when you're looking at a heating curve, that boiling point is the constant temperature at which a liquid becomes a gas. So we bank on the fact that if we're going to be using fractional distillation, the two miscible liquids in question that we want to separate, they would have different boiling points. There should be a good distinction between the boiling points. So water, pure water is like 100 degrees Celsius. Ethanol boils at like 78 degrees Celsius. What piece of apparatus would you use to separate oil from water? Now, oil from water, we now have what we call immiscible liquids, where these two liquids don't mix. And so we use what we call a separating funnel. And that is used to separate two liquids that are immiscible. And I can bring you to a diagram. So here we have the example of the separating funnel. And so these are showing you two liquids that are not capable of mixing. We call them immiscible. So the separating funnel has a stopcock, and what you will do is to open. What we bank on is the fact that one liquid will be more dense than the other. And so the more dense liquid will be at the bottom and the less dense liquid will be at the top. And so you will carefully use a container to collect the more dense liquid, and then we choose another beaker to collect the second. So even though we spoke about oil and water, this is kerosene and water. Why don't they mix? We can talk a little bit about that. Now, water is considered to be a polar substance. Kerosene is a non-polar substance. In terms of dissolving and mixing, we say like, dissolve like. So a polar substance or a polar solvent like water can dissolve a polar solute. So because both of these solvents are one is non-polar, one is polar. They're not going to be mixing, so they're immiscible. So that's one of the things that we bank on for the separating funnel. So we could not use this for ethanol and water because both are miscible. And so remember, one of the things that we say, we look at the properties of the two components of the mixture or the three components, and we use the properties that each component has, and maybe one or the other one doesn't have it, and we use that to separate them. So in this case, what we're going to, and I think there's a question that's going to ask now, what is it that we're banking on? We're looking at the densities. So it is density that we're going to be using to separate these two liquids. So part 2 says, what two properties do oil and water have that make it possible to separate them using the apparatus you named in 2? So we are able to use the separated funnel 1 because oil and water are considered to be immiscible. They do not mix. That's the first thing, right? The second thing, they have different densities. Both are considered to having different densities. Joanne, a forensic scientist, has a sample of black ink from a crime scene, and she wants to find out whether the ink came from Joe's pen or Sam's pen.
No, so we realized that there's a crime that was committed. No, no, so what technique would dry ink use? So she could use the concept of paper chromatography. And the diagram below shows Joanne's result when she did the
concept. So this is the black pen that she found. This is Joe's pen and this is Sam's pen. So in both, these different components will separate out of the ink. So the ink is made up of different components that will have different solubility and different retention factor to the paper, the chromatography paper. So if you look at this, what you will now do is to compare. So you will compare, so when you examine both papers from both parties' pen, we can look at the original black ink and we see that we have 1, 2, 3, 4, 5 components. And so if we look, it says what two factors determine how far each dye in the inks move up the paper. So the two factors that you consider would have been the fact that how soluble the dyes are in the solvent that you use. Also, when it is going up the paper, which one of those dyes are more attracted to the paper? And that those are the two factors that will influence, how far the inks, the components, the dyes in the ink, how far they will move up. The flow diagram below shows the main steps in the extraction of sucrose from sugarcane. Yeah, man, you know them sugarcane, the sugar, yeah, we get it from sugarcane. So the cutting and crushing, then we have precipitation. And after precipitation, think about it and tell me what it is that you think that happens next. So after precipitation, if you said filtration, you would be indeed correct, right? So filtration, you're basically going to separate the solid portion from the filtrate. So you're going to take out any large particles. Then you have vacuum distillation, then followed by crystallization, and then finally what you will have is centrifugation. We're going to be talking a little bit about the various steps, the different processes that we have involved. So we know basically we cut in the sugar cane in Jamaica. We back then, before we were independent, and major areas in the island we had the coverage of sugar cane. It was with monocropping, where as we harvest the sugar cane, we plant back the sugar cane, and we have those cane cutters. Precipitation, and what you will do is to remove the solid portion from the liquid. Then you would have the filtration. Now, a lot of impurities will be in your sugar cane, right? In the mixture, the syrup. So when you filter it, about 85% of that syrup is there, and you filter because you want to remove some of the solid portion that is there. You will have distillation, and that process as well, it removes the water, because you want to get, at the end we're going to be getting solid, because if anybody look at sugar, we get solid. So distillation, what it will do is to cause the water to be removed. Crystallization also helps with the removal of more of this water, and then centrifugation is spinning the contents at high speed, and it uses centrifugal force to remove the solid portion from the liquid portion. And so that liquid portion, in various different steps, we get bagasse. Bagasse is actually used back in the process to help by providing heat, so that will help with the distillation or the process of evaporation, right? What is added to the juice to cause precipitation in the second step? Now, if you wanted to precipitate out, we add what we call calcium hydroxide, and that is what is used to separate, right, the solid portion from. So it helps in two ways. The contents is then neutralized, because the calcium hydroxide is more of an alkaline in nature, so it basically neutralizes the acidic contents of the mixture. What happens during vacuum distillation? So during that process, so remember we spoke about the fact that when you think about that vacuum, you're going to be using the method of evaporation right here, because we want the contents to become more concentrated. Because if you look back on this, about at filtration, that would have been right here, you would have had about 80% of that syrup, and that will contain a lot of water. So when you put it in the vacuum, now you're going to cause this liquid, the water, to evaporate at this point, making it more soluble. And even with crystallization, it becomes even more concentrated and in a solid state. And then finally centrifugation, we separate that solid from the liquid, and so we get that solid portion and we get that liquid portion. So again, thanks for watching. I hope it was beneficial. We looked at questions related to mixtures and separating technique. So in our third video, we're going to be looking at atomic structure. So like, share, and leave a comment as we do our review of the topics, preparing you for your CSEC Chemistry exam. Thank you.